Hello to everyone, my name is Andrea Mattioni, and in this presentation I will present the paper entitled Exponential Stabilization of a Clamped Timoshenko Beam with Actuation on a Tip Mass. This work is in collaboration with Professor Yong-Sin Hu and with Professor Jan Legorec. In this presentation we will first briefly detail the modeling procedure to write the flexible beam with a tip mass in the Porte-Hamiltonian framework. Then we will design a controller that is able to exponentially stabilize the closed-loop system, and in the stability analysis section we will briefly detail the exponential stability proof to conclude about stability of the closed-loop system. Then in the numerical simulation section we will show some simulation results for different selection of the control parameter, and finally we will give some conclusions and some possible future developments. The dynamic equation of the flexible beam are described by the partial differential equation of Timoshenko and with dynamic boundary conditions, since we have a tip mass. We highlight that the torque and force control input affect only the dynamic boundary condition describing the motion of the tip mass. Then to write down the Porte-Hamiltonian representation, we define the state variables, the energy state variables, and for the infinite dimensional part we define the distributed linear and angular momenta, the shear deformation and the angular deformation. And for the finite dimensional variable we define the momenta, the linear momenta and the angular momenta of the tip mass. Then the Porte-Hamiltonian representation is composed by the interconnection of a finite dimensional Porte-Hamiltonian system with an infinite dimensional Porte-Hamiltonian system, where we can see in the operator AM that the contribution of the infinite dimensional part on the finite dimensional parts is due to the term calligraphic C1 calligraphic H, while the contribution of the finite dimensional part on the infinite dimensional part can be seen in the domain definition. Then we remark once again that the input U only affects the finite dimensional dynamic. Then we define the first input operator, calligraphic B1Z, that corresponds to the velocities at the xc equal to L side of the beam and corresponds to the input of our infinite dimensional system, while the second boundary input, calligraphic B2, are the velocity at the xc equal to 0 side and correspond to the homogeneous input. Then the output corresponding to the input YUZ are the restoring force at the x equal to L side of our beam, and we assume that this quantity is measured by some sensors. We now define the control problem that consists on finding a control law that exponentially stabilizes the origin of the closed-loop system, such that the extended state composed by the infinite and the finite dimensional state has a norm that can be bounded by an exponential depending on time. Then to be able to solve this control problem, we define a control law that is composed by two different terms. The first term is depending proportionally on the finite dimensional states P and on the output of our infinite dimensional system, while the second term depends linearly on the time derivative of the output of the infinite dimensional system. And in fact, as can we see from the picture, the controller depends both on the output of the finite and of the infinite dimensional systems that compose our mixed Porte-Hamiltonian system. We now define the closed-loop operator, where we highlight in color the terms that are added by the control law, and in particular we highlight the red term, that is the term that depends linearly on the time derivative of our output, that is normally referred in the literature as strong dissipation feedback. And this time derivative on the right hand side of our equation is a little bit inconvenient for stability analysis purpose, so we bring this red term to the left hand side of our equation, such to be able to define a new set of equations. We therefore do a change of variables, with the new variables eta, such that in the left-hand side we can define the dynamic of the new variable eta, and on the right-hand side we put together the two blue terms to obtain the dissipation term in the eta dynamic. Then, since also the boundary of our operator A1 depends on the variable P, we substitute the change of variables and we make appear on the boundary condition also a dissipation term. So our closed loop system is now written as a power preserver interconnection of an infinite and a finite dimensional system, where the infinite dimensional system also have a dissipation term that we know is strictly connected to exponential stability. Then we define the state variable as belonging to the state space capital X, that is defined as the composition of the L2 square integrable function on R4 and the Euclidean space of dimension 2. Then we equip the state space capital X with the weighted inner product that is defined as the sum of standard L2 norm weighted by the Hamiltonian density calligraphic H, and a second term that is a quadratic form with respect to the finite dimensional variable eta. Then it is possible to prove that the closed loop operator generates a strongly continuous semigroup contraction in the state space capital X, and that also A as a compact resolvent. Then we now introduce some inequalities that afterwards will be used for proving exponential stability. The first inequality is in lemma 3.2, and it tells us that the square norm of the coenergy variable computed at the L side of the beam plus the square norm of the finite dimensional variable eta can be bounded by a quadratic form with respect to the output of the infinite dimensional system and a quadratic form with respect to the inverse of the matrix M multiplying the variable eta. The second inequality is given in lemma 3.3, and we first define a Lyapunov energy functional that is half of the defined inner product on the state space capital X, and then this Lyapunov functional satisfies for a t sufficiently big that a function c of t that goes to infinite for t that goes to infinite, multiplying the energy at times t, can be bounded by the time integral of the coenergy variable square norm of the coenergy variable computed at L plus the time integral of the square norm of the finite dimensional variable eta. We can now introduce the main contribution of this work, that is theorem 3.4, that states that the origin of the closed loop system is exponentially stable. For this theorem, we give a very brief sketch of the proof, and first of all, defining the energy Lyapunov functional, we can take its time derivative and we see that is equal to minus a quadratic form with respect to the output and with respect to the finite dimensional state. Then using lemma 3.2 we obtain a first inequality, and then we take the integral between 0 and t of both sides of this inequality, such to get that the energy at time t is bounded by the energy at time 0 minus the integral from 0 to t of the square norm of the coenergy variables plus the square norm of the finite dimensional variable eta. Then using lemma 3.3 we bound the second term by the energy itself. Then from the last inequality that we get, we know that the energy at time t is bounded by a constant gamma that is strictly lower than 1 multiplying the energy at time 0. That implies again that the norm of the semigroup generated by the closed loop operator is strictly lower than 1, and therefore using a classical semigroup property we can conclude about the exponential stability. Since the exponential decay rate W has been computed with respect to the parameters of the system and the control parameter, we now give in proposition 3.5 a possible selection of the control parameter, and in particular we show that the biggest value of W can be obtained selecting the control parameter as the equality and inequality indicated in proposition 3.5. We now show some numerical simulations, and then we first set the initial condition of the infinite dimensional variables and on the finite dimensional variable, such to get the initial condition at the upper figure in the right side of the slide. Then, according to theorem 3.4, we know that the closed loop system is exponentially stable for any selection of positive definite control parameters matrices. And to obtain our simulation, we select the control parameter according to proposition 3.5. And then the behavior, the closed loop behavior of our system is showed in the figure at the right of our slide. We now show some numerical simulations, and in the solid line we denote the behavior of the norm of the state, while in the dashed line we denote the exponential bound with the corresponding control parameter selection. Then we can see that in blue we have the behavior in case the parameters are selected with respect to proposition 3.5, and we can see that we obtain better performances with respect to other selection, even though this is not an optimal parameter selection. So in this paper we presented the Porto-Hamiltonian modeling of a flexible beam with a tip mass. We then designed a control law that makes appear some dissipation at the boundary of the PDEs. Then we gave the mathematical proof to obtain the exponential stability of the closed loop, and we also gave the numerical simulation of the closed loop system with different choices of the control parameters. Possible future developments could be the formalization of the described control law for a general class of mixed Porto-Hamiltonian system, or the consideration of some nonlinear terms in the set of considered ODEs. Thank you for your attention, and feel free to ask any question.